Well, students, in the last class, we have developed log normal model with which we have obtained a formula for stock price process, which termed a geometric Brownian motion with drift mu and volatility sigma. In this class, we will devise a computational procedure to simulate a stock price process, which is called Monte Carlo simulation. To devise this method, we have to first develop a stochastic differential equation that governs the stock price process. Let us start with what we already know. For a given time t in the interval 0 to capital T, the total return of an investment for the period 0 to T under a continuous compounding scheme with annual interest rate as mu. Remember, generally we take it as R, but here I intentionally prefer to take it as mu, and it is given by S is equal to S naught into e power mu t. This is something which we know right from the beginning of our course. Now you see, this expression can equivalently be written as ds by dt is equal to mu times S, right? For instance, you can directly integrate this to get log S is equal to mu times t plus log of some constant, right? And that can be written as log S by constant is equal to mu t. And if you assume that initially, that is at t equal to 0, the value of S is something S naught, then you can see that this expression is precisely the solution of this problem. This is generally called initial value problem. So if we know the number mu, we know how to obtain the total return in a continuous compounding scheme. And further, if you assume x of t is equal to log of s of t divided by s naught, then this can also be written as dx equal to mu into dt, where mu is a given number. More importantly, it is known to us and it is fixed. So this model, either this or this with the initial condition, is called the deterministic model. Why deterministic? Because there is no randomness involved in it, mainly because this mu is fixed and it is known to us, and this x is also called the log return for the period 0 to small t. Well, this is something which is very simple for us to understand, but unfortunately, deterministic models are inadequate for pricing some risky assets like stocks. Why? Because mainly stocks cannot be predicted like how you can predict the return of a risk-free investment in terms of a interest rate mu. Similarly, you cannot do such prediction for a stock investment, right? The rate of return can be random in the case of risky assets, and therefore we may have to consider this mu as a random variable. And in this case, we turn to get a stochastic model. The idea is to replace mu, which is known to us, by a random variable r. Let us propose to write this random variable r as mu, which is known to us, plus some epsilon, where epsilon varies randomly with respect to time. Often this epsilon varies very rapidly in many applications, including in stocks, and therefore it is not straightforward to replace mu in our deterministic model by this R. Rather, what we will do is to take the deterministic model and add a term which for time being we will call it as noise. We will see how we can model this noise. The main idea is to look for the noise as a Gaussian white noise. Let us give a definition of Gaussian white noise. A stochastic process epsilon t, where t varies in the interval 0 to capital T, is called a Gaussian white noise if for every t in the interval 0 to capital T, epsilon satisfies the following three conditions. One is that for every t, the corresponding random variable epsilon t is normally distributed with mean 0 and standard deviation sigma epsilon for some constant sigma epsilon greater than 0. And as we told, the expectation of epsilon of t for every t is 0, and they are also independent in the sense that expectation of epsilon of s into epsilon of t equal to 0 for every s and t in the interval 0 to capital T, with s is not equal to t. When s is equal to t, then we will have the variance which we assumed as sigma epsilon square, right? So such a stochastic process is what is called the Gaussian white noise. Generally, white noise is physically unrealistic since its mean square value blows up to infinity. An alternate way of handling this situation is to use Wiener process, which is also called Brownian motion, which can be formally represented as a stochastic integral of a white noise process. We will not go into the details of the theory behind the white noise and how to write a Wiener process as an integral of the white noise. Rather, we will simply accept this result. That is, a Gaussian white noise, if you take and integrate it over an interval 0 to t, what you get is what we call as Wiener process. Also, this integration is a stochastic integral, which we will not go into the details of how to define the stochastic integral and so on. If you want to quickly recall, the integral of a stochastic process over an interval a to b can be written as the limit as delta t tends to 0 sigma z of ti into delta ti. That is, you discretize the interval a to b into some pieces with length being delta ti, and then write this term and then take delta ti tends to 0, and if that limit exists, then that limit is denoted by this symbol, and the limit is taken in the sense of the mean square sense. We will not go into the details of all this, but we will simply accept it with some knowledge in the basic probability and stochastic processes. But rather, in our course, we will try to approximate the Wiener process using this idea. How we are going to do this? Let us see. You look at the definition of this stochastic integral. As I told you, we will first partition the interval 0 to t into n subintervals with length being delta t. So we are uniformly partitioning the interval where tk plus 1 can be written as tk plus delta t, with the understanding that T of 0 equal to 0 and T of capital N equal to capital T. Okay, so we are basically subdividing the interval 0 to T into capital N equal parts. And this is T0, T1, T2, and so on, Tn minus 1, and this is Tn. And we will write WTK as this term. Okay, remember this epsilon is what is the Gaussian white noise. In our study, we will take this Gaussian white noise as the standard normally distributed random variable for each Tk, and then this expression can be written as Wk plus 1 equal to Wk plus epsilon into Tk into root delta T. Remember, we should have taken just delta T here because this is how we intend to define the stochastic integral, but it doesn't matter because anyway we are going to take delta T tending to 0. Therefore, it doesn't matter really whether you take delta T or root delta T, but we prefer to take root delta T here for some purpose, which I will tell you when it comes on our way. But time being, you keep in mind that we are defining the process Wk in this way. Now, how we go is we start with W0, which we will take as 0. Then W1 is defined as W0, which is 0, plus you generate a random sample, which is normally distributed random variable, and that we will denote as epsilon T0 times root delta T. Remember, delta T is given to us, where when we were discretizing the interval 0 to capital T, we have fixed the capital N, and from there we obtained delta T, right? So this is known to us, and this is generated as a normally distributed random number, and from there you can obtain W1. Again, from there you can get W2, which is equal to W1 plus, again you generate a random number which is normally distributed with mean 0 and variance 1. That is also important. Okay, into root delta T. So remember, we also make sure that while selecting this epsilon T1, we never use any information about epsilon T0, and similarly for the other terms also. That is because we need this epsilons to be independent. That is a part of the Gaussian white noise definition, right? So we'll keep all this in mind while we are generating this random variables epsilons. So in that way, we are getting the numbers W1, W2, and so on. This is called the random walk. Let us summarize what we did so far. Our interest is to model a stochastic differential equation for a stock price process. This is because we are interested in obtaining a numerical procedure to simulate stock price process. For that, we started with a deterministic model, and we wanted to add randomness into it. While doing it, we propose to add Gaussian white noise into the system, but that is not quite easy to handle. Therefore, we used a result which says that integral of the Gaussian white noise over the interval of interest is nothing but the Wiener process or the Brownian motion, where the integral has to be interpreted in the stochastic integral form, which gives us an idea to adopt an approximation, and that approximation naturally leads to what is called a random walk. In fact, you can see that from here, you can write it as wk minus 1 plus epsilon tk minus 1 plus epsilon tk times delta t square root. And again, you can apply this expression for wk minus 1 to get wk minus 2 plus epsilon tk minus 2 plus epsilon tk minus 1 plus epsilon tk times square root of delta t, right? You can go on like this till you reach w naught, which we have taken as 0, plus epsilon of t naught to epsilon tk times square root of delta t, right? So that is what we have proposed to take as wk here, which is in a sense approximation to the stochastic integral. In fact, we can simulate this random walk in the procedure which I explained previously. That is, you start with w naught equal to 0, that is what you can see here, and then you take w1 as w naught, which is 0, plus you generate a random number which you call as epsilon t naught times root delta t, and that is what you take as w1, and then w2 is again w1 plus generate another random number which you call as epsilon t1, which is normally distributed with mean 0 and variance 1. You can use any software like MATLAB to generate such random numbers into delta t. Like that, you can go on in time with some discrete time level to generate this random walk sample. Since I have taken here a large number of sample points, that is, I have taken n is equal to 1000 here, you rather see this curve more in a continuous way, and this is nothing but the epsilon t case, and this is a typical visualization of a white noise. Rather, we can say that a discrete form of white noise, which is also called color noise sometimes. In fact, we can check that WTK, which is defined at discrete time level, in fact satisfies the properties of the Wiener process. How will you see that? Let us check the properties of Wiener process for the W case that we have defined as random walks. First, let us take some j and k as some integer between 0 and n such that j is less than k. You can write wk is equal to wj plus sigma I is equal to j to k minus 1 epsilon t I into root delta t, right? So that comes directly from the way you have defined W case. And from there, you can rewrite and get this expression. You can see that Wk minus Wj is written as the sum of normally distributed random variables with mean 0 and standard deviation 1, right? Therefore, Wk minus Wj itself is a normally distributed random variable. And you can also see that the expectation of xk minus xj, which is nothing but I equal to j to k minus 1, expectation of epsilon of t i's, right, into root delta t. But we know that epsilons are standard normal distributions with mean 0. Therefore, this is 0, and that gives you even expectation of xk minus xj is 0. And you can also see that the variance of xk minus xj equal to tk minus tj. How will you see this? Well, you can write variance of xk minus xj is equal to expectation of sigma I is equal to j2 k minus 1 epsilon of ti into root delta t, right? Now, by definition of epsilon, we know that expectation of epsilon xk into epsilon xj is 0. This is one of the assumptions that we had in the Gaussian white noise definition, as long as k is not equal to j, of course. Therefore, variance of xk minus xj will only have expectation of sigma I is equal to j2 k minus 1 epsilon ti square into delta t, right? All other terms will vanish, and that will happen to be sigma I equal to j2 k minus 1 expectation of epsilon ti square into delta t. I'm just pulling out delta t out. But since the mean of epsilons are 0, you can see that this is nothing but variance of epsilon of ti, right? And that is assumed to be 1 because these are normally distributed random variables with variance 1. Therefore, we can see that all these are 1, and that leads to variance of xk minus xj equal to tk minus tj. You should parallelly compare all these properties with the definition of Wiener process and see that these are the properties that are needed to be satisfied for a Wiener process. If you recall, while defining the random walk, we purposely took this term as root delta t, and there I have remarked that we will come to this to mention what is the reason behind taking root delta t instead of delta t. That is precisely to make this term quite comfortable to achieve this property. Further, for any, this is t naught less than or equal to tk1, some number k1 between 0 to capital N integer, and similarly k2, k3 and k4 you choose such that tk1 is less than tk2, is less than tk3 and is less than tk4. Then you can see that the random variables wtk2 minus wtk1 and wtk4 minus wtk2 are independent. This you can clearly see because this is written as sum of epsilon ti's, where I runs from tk1 to tk2, right? Similarly this, and none of them are going to sit in the other sum. Therefore, since they are independent, these two will obviously be independent. So these are the main properties that a Wiener process should satisfy, and we have seen that all these properties are satisfied by our random walk process also. Only one property that we have to check is the continuity property that can also be checked easily, but little manipulations one has to do, but I will omit that discussion. But we will simply agree that as we take delta t tending to 0, even this random walk will become a continuous curve, and therefore you can see that as t tending to 0, we will get a Wiener process out of the random walk process that we have defined. And we will generally take this Wiener process as W. Also recall that we have defined the random walk as Wk plus 1 is equal to Wk plus epsilon Tk into root delta T, right? Now, you give me any T in the interval 0 to capital T, what I will do is I will define W T plus delta T. It's not only that Tk to Tk plus 1, which is defined as Tk plus delta T, right? You give me any T, from that T, I will add delta T and obtain the value of that random variable as Wt plus epsilon T into root delta T, right? I can just generalize this idea to any T, not only those Tks which are sitting in our partition. It can be adapted to any T in the interval 0 to capital T and write Wt plus delta T like this. Remember, Wt means W of T. Therefore, Wt plus delta T means W of T plus delta T. Therefore, by taking delta T tending to 0, formally, without worrying about the mathematical technicalities, we can see that this expression can be symbolically written as dw, where dw is a infinitesimal change in w, is equal to epsilon t into dt, where dt is also infinitesimal change in t, and the corresponding infinitesimal change in w is denoted by dw. So this is what we can obtain by formally taking the limit in this equation, and this is called the Wiener process. In this derivation of the Wiener process model, we have not taken care of the mathematical technicalities more rigorously because we have no assurance of the limiting operations to be defined, right? But it is just a formal derivation which gives us a intuitive idea of how these models are coming out.
However, it is important to justify the existence of these limits in order to give meaning to these operators, but for our course, we will omit these discussions.
Now we propose to put the noise term in our stochastic model as epsilon t into root dt, which can also be represented by this symbol dw, and that terms to be the generalized Wiener process, where we want to put the noise term as some constant times dw. Remember, we already had mu into dt, which is coming from the deterministic model. And now we have introduced this term, which is coming due to the randomness in the process, which we first started it as a Gaussian white noise, and then we have replaced it as a derivative of the Brownian motion. Remember, there are many things that we have not mathematically justified. For instance, we know that Brownian motion is nowhere differentiable, but you can see that dw is sitting here.
But you should see it just as the white noise because W is written as the stochastic integral of the white noise only, right?
Therefore, all these have to be kept in mind. But in this course, we will not get into the mathematical details or behind the meaning of all these terms. Rather, we will take them as intuitive meanings. Recall that we have taken x as log s of t divided by s naught, where s naught is the stock price at time t is equal to 0, and s of t is the price of the stock at any future time t in the interval 0 to capital T. Capital T may be interpreted as the time at which we want to exit from the stock. Now, from 0 to capital T, our interest is to simulate the stock price process, and that is now can be written as d log s is equal to mu into dt plus sigma into dw, because we have derived the equation for x as dx equal to mu into dt plus sigma into dw, right? Generally, mu is a constant given to us, and sigma, which is greater than 0, is also a constant given to us, and this w is a Wiener process. And this model is called the generalized Wiener process. It's either this or this, with drift mu and volatility sigma. You can formally integrate on both sides of this equation to get log of the stock price as mu into t plus sigma into wt plus the log of the initial price. And if you recall, this is what is called the geometric Brownian motion. You can take exponential on both sides to get this expression. If you recall, this is what we have also obtained from the log normal model. So in a sense, you can see that the stock price process obtained through log normal model is precisely coming as a solution to this stochastic differential equation. Now, another interesting thing to observe is that you can differentiate this term, right? So how will you do? D log s may be written as ds by s, right? So that may tempt us to write this equivalently as ds is equal to mu s dt plus sigma s dw. But unfortunately, this is not correct. Rather, this can be written in this form where everything is okay. That is, ds is equal to some mu times s dt plus sigma s dw, but this mu is slightly different. You see, mu is given by your previous mu plus sigma square by 2. This is a very interesting fact as far as the calculus on a random variable is concerned. There is a subtle difference between calculus on a function and calculus on a random variable. We have a formula for this, which is called Ito formula or Ito lemma, that we will see in the next lecture.